Okay. Welcome to another video on numerical solutions to equations. As I emphasized in the video before, this topic contains questions from a range of other topics. So the next idea is further trigonometric graphs. With further trigonometric graphs, I am talking about the graphs of sec x, um, cosec x, and cot x. Okay, in order to understand these three graphs, what I'm going to do is I am first going to draw the graphs of cos x, sin x, and tan x for you, and below that I'm going to draw the graph of cosec x, sec x, and cot x. Okay, so I am first drawing the graph of cos x because that is the graph that converts to sec x. Now I'm drawing them in degrees. You can obviously draw them in radians as well. Okay, I am just going to copy paste this, but let me just first draw. Okay, so I am going to say that I am going to draw these for you. Okay, so the graph of cos x looks something like this. It starts at 1, then it goes to 0, and then it also goes to -1, which I'm going to mark here, and so it's something like this. Okay, it's a little to the left and right, that doesn't matter. I can move 180 around. So that is what the graph of cos x looks like. Let me just draw that again. Okay, so remember that sec x is simply 1 over cos x. So every value of cos x, now cos x takes on the value 1, 0, and -1. So each of these values is going to get divided by 1. So let's talk about this first value. So 1 divided by 1 gives me 1. So sec x is also going to start at 1. Then the next value I have is 0. So I'm going to say 1 divided by 0. That gives me infinity. So I'm going to create an asymptote here and say that the curve goes to infinity, so that the curve looks something like this. Okay. Okay. Then at this point I have -1, so I'm going to say 1 divided by -1. That gives me -1. So sec x is also at -1. Okay, on both these then I have an infinity at 270. Now how do I know that the curve is going to be negative? If cos x was negative throughout this portion, 90 to 180, then sec x must be negative, and it would look something like this. So that is how you draw the graph of these inverse trigonometric functions. Again, at the end I have a 1, so I'm going to place that here and draw a curve like that. So that is the graph of sec x. Similarly, I can draw the graph of sin x and then show you the graph of, this is the graph of sin x that I'm drawing. It's going to look something like this, and then something like this. Okay, slightly distances are a little messed up, but that's part of the sketching. You don't need to be exact. Now the first thing that I would decide is it's at 0, 0, 0. That means I'm going to have three asymptotes, one at 180, the other at 360, and the other itself at 0, because all of these values of sin x are basically going to get so this is y equals to sin x, and cosec x is 1 over sin x. At This value is 1, so 1 divided by 1 will also give me 1, and 1 divided by minus 1 will give me that. So the graph of cosec x will look something like this. Yeah, okay, and this one will look something like this. Then if you imagine tan x, it already has asymptotes at 90 and 270, and the graph of tan x looks something like this. It starts at 0 and then goes there, then it goes there, and then it goes there, and then it goes down again. So remember that I am, again, when I'm drawing cot x, I am thinking about 1 over tan x. So I'm saying that this has to be, well, this color could be a little darker. I just go and make this a little darker. Yeah, that works. Okay, so I know that the asymptotes are now at this point, and that point. So I'm going to draw the asymptotes at 180 and 360. Okay, then the existing infinities, if I talk about this value, so at 90 it was at infinity, so I'm going to say 1 over 90, 1 over infinity, and 1 over infinity is basically 0. So the graph comes down to 0 at this point. Okay, and it's at infinity at 0 as well. Throughout, from 0 to 90 the graph was positive, from 90 to 180 the graph was negative, so the cot x graph would look now something like this. Okay, and the other graph would also look something like this. So that is the graph of cot x. Ideally you should remember all of these, but you can always derive them using your normal trigonometric graphs. Now, why are these graphs important? Because when you see this question, a lot of these numerical solutions questions will have this. It says by sketching the graphs of y equals to cosec x, and this show that the equation this has exactly two real roots in the interval 0 to pi. So I know that I can draw the graphs from 0 to pi, which means 0 to 180. Now I have to be a little careful. Why? Because I have to draw pi over 2 and pi. Let's call that pi. Cosec x is basically 1 over sine x. So the graph, as we saw earlier, is that there's an asymptote at pi or 180. Why? Because there was an asymptote, sine 180 is 0 and sine 0 is also 0, and this graph is at 1. I'm going to mark 1 a little lower because I still need to draw the other line. So it's going to come like that and go like that. That is the graph of cosec x between 0 and pi. Now, I want to show you that there's only one root in the interval. I want to draw this graph. Now, this graph is a little tricky. It says x pi minus x. I don't know the nature of this graph, but when I expand it, I see that this is actually a quadratic graph. A quadratic graph needs to have a turning point. It also needs to have x-intercepts. So what I feel is that I could calculate the turning point either by putting it on a calculator, or say that the x-coordinate of the turning point is minus b over 2a. So minus pi over 2 times minus 1. That tells me that the turning point is at pi over 2. But what's the value of y at the value x, pi over 2? So let's calculate that. Okay, so this becomes pi squared over 2, pi squared over 2 minus pi squared over 4. Okay, why am I doing this here? I can write it here. So pi into pi over 2 minus bracket pi over 2 whole squared. Okay, so I get 2.467. So I know that the turning point is somewhere here, and if I look at the x-intercepts, they are at 0 and pi. So I know that my required graph, let's draw that in green, will look something like this. It's a quadratic graph, so it goes like that. So what did I have to prove to you? That there are two real roots. So I'm going to write two intersection points, means two real roots. Okay, that is the first part of the question. Now for the second part of the question, it says show that the equation this can be written in the form that. I think that's an easy question on trigonometry. I just need to convert everything to sine x. I'm going to multiply that, and I'm going to open this bracket up as well. X pi minus x square. I know that I need to cross multiply, so I'm going to say that x pi sine x minus x square sine x, 1 plus x square sine x equals to x pi sine x. And I think I have my answer, 1 plus x square sine x over pi sine x equals to x. That's 2. It says the real roots of the equation this in the interval 0 to pi are denoted by alpha, show, and where alpha is less than beta. So these two values are called alpha and beta. If these two values are called alpha and beta, use the iterative formula this to find alpha correct to 2 decimal places, give the result of each iteration correct to 4 decimal places. Now what I want you to notice here is that the question has given me no starting value, but I can see from my graph that the alpha is somewhere between 0 and pi over 2. Pi over 2 is basically on my calculator is 1.57. So I could use any value between 0 and 1.57. Let's say I go with 0.7. So I say that my starting value for my iterative process, that's part 3, and that's a of part 3. So I'm going to say that the first value of my iterative process is 0.7. I'm going to say 0.7 equals to, and then I'm going to construct my expression 1 plus answer squared into sine of answer bracket pi into sine of answer again. Okay, everywhere that I have x, I've put an answer. So that gives me, oh, my calculator is not in radians, I need to do that. Yeah, and I'll need to do this again because the calculator didn't pick that up. That you have to be careful about that. I'm going to write this again, 1 plus answer squared into sine of answer pi into sine of answer. Okay, so x1 was this, x2 is 0 0.65, 0 1, x3 is 0 0.6604. I have to round off to 3 decimal places, 0 0.65, 0 0.66, then 0 0.6577. That rounds off to 0 0.66 again, and that should also round off to 0 0.66. So I can say that my root is 0 0.66. So alpha equals to 0 0.66, and that is the result from my iterative process. Then reduce the value of beta correct to 2 decimal places. Beta is the other root. Now what I want you to understand is that both of these graphs are actually symmetrical. Why? Because you remember that sine x goes like that, which means that it was symmetrical on both sides. So is this quadratic graph, you know that it's on the turning point, it's symmetrical on both sides. So can I say that the distance from 0 to alpha is the same distance from beta to pi. Why? Because there is a symmetry and I know that those two are x-intercepts. So what is the distance from 0 to alpha? That's the value of alpha itself, distance from 0 to alpha. Why am I doing all of this? It says reduce the value of beta correct to two decimal places. So I'm trying to find beta by deducing it, not by calculating it. Again, if I wanted to calculate, there was a simple solution. I could have taken a value between pi over 2 and pi, let's say greater than 1.7. I could have taken 2.0 and it would have given me the other root if I had done the iteration again. So that's also something that you should know. But I'm deducing, so I'm going to say that this is the distance. Okay, subtracting this distance from pi will give me beta. Pi minus 0.66. Okay, so 3.142 minus 0.66, and that gives me 2.482. I'm just going to write 2.48 correct to three significant figures or two decimal places, and those two should be my final answers. I hope this video was productive. It had inverse trigonometric graphs. There are two more difficult questions on numerical solutions to equations, which will be part of the next video. Please like and subscribe and continue watching for more videos. Thank you.